Hi, welcome back to my class in Algebra. For today, we will continue with solution of inequalities. But today, we will take up solution of inequalities that involve quadratic expressions. When, when you are solving linear inequalities, you, you are like solving a linear equation. But when you are solving inequalities that contain quadratic expressions, you have to consider two cases. For an example, consider the following. Solve, that is, to find the values of x that will satisfy the given inequality. And you know that from our past lesson, we learned that the solution of inequality is a set of values, is a set of infinitely many values for the variable in the inequality. Unlike when you are solving a linear equation, in one variable there is exactly one value or one solution for the linear equation in one variable. So in this example, we solve the inequalities, that is, we find all the values of the variable that will satisfy the given inequality. Show the solution in diagram. That is, we represent the solution in the one-dimensional space or the real line. Give the solution using interval notations. We know from our past lesson that interval notation is a way of writing a set. And we have learned three types of interval notations: the open interval, in which both endpoints are excluded from the set; the closed interval, where both endpoints are included in the set; and the half open interval, where one of the endpoints is excluded from the set. This is our first example. We find all the values of x such that 2x squared plus 7x minus 15 is less than equal to 0. It is in this type of example involving quadratic expression that we will consider two cases. And this is a quadratic expression because the highest exponent of the variable x is 2. If the highest exponent of a variable that appears in your equation is 2, that expression is a quadratic expression. And since the variable involved in the quadratic expression here is x, we say that this expression 2x squared plus 7x minus 15 is quadratic in x. Now, the first steps to solve a quadratic inequality is to check if the quadratic expression is factorable. So we will try to factor this out using trial and error. And we start by factoring the first term, 2x squared. Since 2 is a prime number, the only factors or the only numbers that can divide 2 are 1 and 2. And x squared can be factored in as x multiplied by x. And 1 multiplied by x is x. If the coefficient is 1, it is customary that we do not write the coefficient 1 anymore. So we check 2x multiplied by x is 2x squared. After you factor out the first term, factor the constant term. That is the term without the variable x. The constant term is minus 15. And it is in factoring negative 15 that we would use trial and error. because negative 15 has many sets of factors. One possibility is negative 5. One set of factors for negative 15 is negative 5 and positive 3. Another set of factors for negative 15 are 3 and negative 5. These are the possible sets of factors for negative 15. Negative 15 is equal to negative 5 multiplied by 3. Negative 15 is also equal to positive 5 multiplied by negative 3. And negative 15 is equal to positive 15 multiplied by negative 1. We should delete 3 and negative 5. These factors are the same as negative 5 and 3. And the last set of factors for negative 15 is 1 and negative 15. Now we want to check which of these factors would work out. We start with negative 5. We start with positive 5 and negative 3. You can write plus 5 here or plus 5 here. I will write plus 5 here. And I will write negative 3 here, 2x minus 3. So for the factors of negative 15, I used 5, positive 5, and I added 5 to x, x plus 5, and negative 3, which I subtracted from 2x, 2x minus 3. Negative 3 multiplied by positive 5 is negative 15. Now we check if these are the factors of the quadratic expression 2x squared plus 7x minus 15. And to check, we must get the middle term of the quadratic expression 7x. And we do the checking by cross multiplication. 5 multiplied by 2x is 10x. And x multiplied by negative 3 is negative 3x. And 10x minus 3x is equal to 7x. And the middle term is 7x. If you get the middle term in checking, that means your factors are correct. The factors of the quadratic expression 2x squared plus 7x minus 15 are 2x minus 3 and x plus 5. If you did not get the middle term in checking, you try the other sets of factors. But since we get the middle term of the given quadratic expression, then our factors are correct. We now write the left-hand side as the product of 2x minus 3 and x plus 5. The quadratic expression 2x squared plus 7x minus 15 is equal to the product of 2x minus 3 and x plus 5 less than equal to 0. And we now find the values of x such that this product is negative, less than 0, or equal to 0. And there are two cases by which the product of two numbers will be less than 0 or negative. And those are the two cases that we will consider. The product of two real numbers, say A and B, is less than equal to 0 or negative or 0 if A, the first factor, is negative, less than equal to 0, and the second factor B is positive, greater than equal to 0. Because if you multiply negative by positive, the product is negative. The product AB would be less than equal to 0 or negative. And this is the first case that we will consider, where A now is 2x minus 3 and B, the second factor, is x plus 5. And this is the first case. We take A less than equal to 0, where A is 2x minus 3. And the second factor B, we take as greater than equal to 0, where B is the second factor, x plus 5, greater than equal to 0. If 2x minus 3 is less than equal to 0, that is 2x minus 3 is negative, and x plus 5 is greater than equal to 0, that means x plus 5 is positive, and you multiply 2x minus 3, which is negative, by x plus 5, which is positive. The product will be negative or less than equal to 0. And the next step is we solve each of these linear inequalities. It is now a linear inequality because 2x minus 3 is a linear inequality because the exponent of x here now is 1, and x plus 5 is also a linear inequality because the exponent of x here is 1. And as I said, we would solve each of these linear inequalities and we will get the intersection of their solutions because both of these inequalities must be satisfied. We start by solving the first linear inequality, 2x minus 3 less than equal to 0. And as we did in the past lesson, solving a linear inequality is like solving a linear equation. The variables should be at one side of the equation and all the constant terms should be at the other side of the equation. And so here, negative 3, we transpose to the right hand side of the inequality, or you add plus 3. You add 3 to both sides of the inequality, and that is by addition property of inequality. If you add 3 to both sides of this inequality, the inequality remains true. But we simply transpose negative 3 to the right hand side, and when we transpose, we take the opposite side of the term. So when we transpose negative 3 to the right hand side, it becomes positive 3. And at the left hand side, we are left with 2x less than equal to negative 3 to the right hand side becomes positive 3. And in the solution of linear equation or linear inequality, the coefficient of the variable should be positive 1. But here the coefficient of x is 2, so to remove 2 from the coefficient of x, we divide both sides by 2. Since we are dividing by a positive number 2, the inequality remains the same. And that is another property of inequality. If you divide both sides of an inequality by positive real number, the inequality remains the same, less than equal to. From the left hand side, 2 divided by 2 is 1, or we simply cancel out 2 from the left hand side. At the right hand side, we have 3 over 2, or that's 1.5. And this is the solution of the linear inequality 2x minus 3 less than equal to 0. All the values of x that are less than equal to 3 over 2 are solutions of this linear inequality. And we represent this in diagram. You locate 3 over 2 in the real line. The solution of this linear inequality is x equals 3 over 2 and we indicate that 3 over 2 is included in the solution by using a shaded circle. And the other solutions of this linear inequality are those values of x that are less than 3 over 2. This is 3 over 2, and the real numbers that are less than 3 over 2 are those real numbers to the left of 3 over 2. Those real numbers to the left of 3 over 2 up to negative infinity are solutions of 2x minus 3 less than equal to 0. Next, we solve this, the second linear inequality, x plus 5 greater than equal to 0. And we transpose positive 5 to the right hand side, or you may subtract 5. Subtract 5 from both sides of this inequality. And the inequality sign will remain true. It will remain greater than equal to 0. Because that's a property of inequality. If you subtract the same constant from both sides of inequality, the inequality sign remains the same or remains true. But we simply, again, transpose positive 5 to the right hand side. And when we do that, we take the opposite sign of the term. From positive 5, you transpose it to the right, it becomes negative 5. And at the left hand side, we have x greater than equal to, transpose positive 5 to the right, it becomes negative 5. And these are the solutions of this linear inequality x plus 5 greater than equal to 0. X is equal to negative 5. So x equals negative 5 is one of the solutions. And we represent that in this diagram. This is negative 5, 0, negative 1, negative 5. To indicate that x equals negative 5 is a solution of this linear inequality, we indicate that by shaded circle. And all the real numbers that are greater than negative 5 are also solutions of this linear inequality x plus 5 greater than equal to 0. And this is negative 5. The real numbers that are greater than negative 5 are all real numbers to its right, up to positive infinity. The solution of this linear inequality is represented by this diagram. The solution of x plus 5 greater than equal to 0 are those values of x from negative 5 and all the real numbers greater than negative 5. Those real numbers are to the right of negative 5 up to positive infinity. And the solution of this linear inequality 2x minus 3 less than equal to 0 are those real numbers from 3 over 2 and less than 3 over 2, represented by this arrow to the going to the left up to negative infinity, because all the real numbers to the left of 3 over 2 are less than 3 over 2. And 3 over 2 is also a solution. That is why we use small shaded circle to indicate that 3 over 2 is a solution. Now for the solution of case 1, where 2x minus 3 is less than equal to 0 and x plus 5 must be greater than equal to 0. These two inequalities must be satisfied. And those values of x that satisfy both of these linear inequalities are those real numbers that are common to these diagrammatic representations of the solutions of these two linear inequalities. And by inspection of this diagram, you can see that the real numbers common to these solutions, to these arrows, are those real numbers from negative 5 up to 3 over 2. The real numbers from negative 5, including negative 5, up to 3 over 2, including 3 over 2, is the solution of case 1, where the first factor 2x minus 3 is negative and the other factor x plus 5 is positive or 0. So we write the solution of case 1 using interval notation. And when we write the interval notation, we always start from the left end point, which is negative 5, followed by the right end point, which is 3 over 2. And because negative 5 is included in the solution as indicated by this small shaded circle, we use a bracket for negative 5. And for the right end point, we also use a bracket because 3 over 2 is a solution as indicated by this small shaded circle. Thus, for the right end point, we also use a bracket. And this is the solution of case 1. All the real numbers between negative 5 and 3 over 2, including the endpoints, are solutions of case 1, where values of x were 2x minus 3 less than equal to 0 and x plus 5 greater than equal to 0. And when you multiply them, the product or the quadratic expression is negative less than equal to 0. Now we consider case 2. In case 1, we consider the product AB less than equal to 0 for where A is less than equal to 0 and B is greater than equal to 0. Now the product of two real numbers A and B is also less than equal to 0 if the first factor A is greater than equal to 0, positive, and the second factor B is negative or less than equal to 0. If A is positive and B is negative, and you multiply these two real numbers A, B, the product is negative. In case 1, we consider A less than equal to 0 and B greater than equal to 0. Because if A is less than equal to 0, negative, and B is greater than equal to 0, positive, the product AB is also negative. For case 2, we now take the first factor A greater than equal to 0, where A is the first factor of the quadratic expression given. The first factor is 2x minus 3, and we now take this as positive or greater than equal to 0. And the second factor, B, is less than equal to 0. In our example, B is the second factor of the given quadratic expression. That is, the second factor is x plus 5, and we take this as negative or less than equal to 0. And we solve this linear inequality separately, and we take the intersection of their solution. We take the solutions common to the solutions of these two linear inequalities. And we start from this linear inequality 2x minus 3 greater than equal to 0. We take negative 3 to the other side of the equation, that is by transposition, or by addition property of the inequality, you add 3 to both sides of the inequality, and the inequality sign will remain true. If we transpose negative 3 to the right hand side, it becomes positive 3. And at the left hand side, we still have 2x. And the inequality sign remains true, greater than equal to 0. Greater than equal to 3. We transpose negative 3 to the other side, becomes positive 3. At the left hand side, we are left with 2x. And the inequality sign remains true, that is 2x is greater than equal to 3. And now we divide both sides of this linear inequality by 2. At the left hand side, we can cancel out 2 because 2 over 2 is 1. Hence, we get x greater than equal to 3 over 2. And we represent this solution of this linear inequality 2x minus 3 greater than equal to 0 in a diagram. Our diagram is a one-dimensional space that consists of the real line. And we approximate that this point is 3 over 2. The solution of 2x minus 3 greater than equal to 0 are those real numbers that are greater than equal to 3 over 2. With the equal sign, it means that 3 over 2 is one of the solutions, and we indicate that by small shaded circle. Other solutions are the real numbers that are greater than 3 over 2. In this diagram, the real numbers that are greater than 3 over 2 are the real numbers to the right of 3 over 2. Up to positive infinity. Hence, all the real numbers that are greater than 3 over 2, including 3 over 2, will satisfy this linear inequality 2x minus 3 greater than equal to 0. If you take any real number, including 3 over 2, or any real number greater than 3 over 2, and you substitute here that value of x, and this 2x minus 3 will be greater than or equal to 0. Now we solve this linear inequality x plus 5 less than equal to 0 by transposing positive 5 to the right hand side, and it becomes negative 5. At the left hand side, we are left with x. If we transpose positive 5 to the right hand side of the inequality, it becomes negative 5. Thus, the solution of the linear inequality x plus 5 less than equal to 0 are those real numbers that are less than or equal to negative 5. And with this equal sign, it means that negative 5 is also one of the solutions. And we represent the solution of this linear inequality x plus 5 less than equal to 0 in the diagram. Suppose this is the point negative 5. Because negative 5 is a solution, we indicate that in the diagram by a small shaded circle. And the other solutions of x plus 5 less than equal to 0 are the real numbers that are less than negative 5. And in the diagram, the real numbers that are less than negative 5 are those real numbers to the left of negative 5, and we indicate that by an arrow going to the left. Up to negative infinity. Now, for case 2, the solutions are those values of x that will satisfy both of these inequalities. Both of these inequalities must be satisfied by the values of x. And those values of x that will satisfy both of these inequalities are those solutions, those real numbers that are common to the solutions of this linear inequality represented by this solution, by this diagram, by this arrow, and the solution of this inequality represented by this arrow. But you can see that there are no real numbers that are common to this solution of this linear inequality and to this solution of this linear inequality, because the arrows go in opposite directions, and so there is no solution for case 2. There is no value of x that will give you 2x minus 3 greater than equal to 0, and at the same time that will satisfy this x plus 5 less than equal to 0. And we write the solution for case 2 as empty set or null set, denoted by this symbol. The solution for case 2 is represented by this Greek letter P to denote empty set or null set. Now, the solution of the given quadratic inequality is the union of the solution of case 1, which is given by the closed interval negative 5 and 3 over 2, and the solution of case 2, which is an empty set. Thus, the solution for example 1 is this closed interval negative 5 3/2 union the solution of case 2, which is the null set or empty set. But from your study of sets, the union of a set and the null set is equal to the set. The union of a set and an empty set is the set. Thus, the union of this closed interval and the null set is equal to is equal to the closed interval -5, 3/2. Now we will check if this solution is correct. All the real numbers between -5 and 3/2, including -5 and 3/2, are solutions. And we will now check if this solution is correct. Again, the given quadratic inequality is 2x squared plus 7x minus 15 less than equal to 0. And we consider two cases because there are two cases by which the product of two real numbers can be negative. And in the solution, we first factored out the quadratic expression 2x squared plus 7x minus 15. And we obtained the product of two factors that should be less than equal to 0. That is why we consider two cases, because there are two cases by which the product of two real numbers can be negative. And the solution of the two cases, the union of the solutions of the two cases is the solution of the given quadratic inequality. And for this particular example, our solution is the closed interval -5, 3/2. And the solution is represented by this diagram. The solution of this quadratic inequality are the set of real numbers from -5, indicated by this shaded circle, and up to the real number 3/2, because we have a close at the right end point, which means 3/2 is a solution. And all the real numbers between -5 and 3/2 are solutions, represented by this line. Now, to check if the solution is correct, you take any real number, you take any number between -5 and 3/2, including -5 and 3/2. And then you substitute the real number in this quadratic expression, and you check if when you simplify, you will get a number that is less than equal to 0. I will take 0. 0 is in this closed interval, or 0 is between -5 and 3/2. I will take x equals 0. If x equals 0, we have substitute x equals 0 in this quadratic expression. You have 2 times 0 squared plus 7 multiplied by 0 minus 15. And we want to check if this is less than equal to 0. Hence, we put a question mark above the inequality less than equal to 0. But 0 squared is 0, multiplied by 2 is 0. So this term will go, 7 times 0 is 0. So the second term will also go. And we are left with -15. And -15 is certainly less than 0. The inequality less than equal to 0 is satisfied. In particular, -15 is less than 0. I will take another real number between -5 and 3/2. I will take x to be equal to -1/2. If x is -1/2, you substitute that value of x in this quadratic expression and simplify, and then you check if the real number you would get is less than equal to 0. We have 2 times x, -1/2 squared. Plus 7 times x, -1/2. Minus 15. And we want to check if this when simplified is less than equal to 0. The square of negative is positive. The square of 1 is 1, and the square of 2 is 4. Thus, the square of negative 1/2 is positive 1/4. And multiply by 2, that's 1/4 multiplied by 2, you get 2/4, or in lowest terms, 1/2. We have positive times negative is negative. 7 multiplied by 1 is 7/2. Minus 15. We want to check if this is less than equal to 0. The denominator of 15 is 1. So the LCD is 2. For you to have a denominator for negative 15, you multiply negative 15 by 2/2. For us to have the common denominator of 2, we multiply negative 15 by 2/2. Now the common denominator is 2. And the numerator is 2 divided by 2 is 1, multiplied by 1 is 1. Minus 2 divided by 2 is 1, multiplied by 7 is 7. Minus, we have 2 divided by 2 is 1, multiplied by 15 times 2 is 30. And we want to check if this is less than equal to 0. Or you may have common denominator is 2. We have 2, numerator is 1, minus 7, minus 15 times 2 is 30. Now we get the difference of the numbers in the numerator. We have 1 minus 7 minus 30 is negative 36/2. 1 minus 7 minus 30 is negative 36/2. Negative 36/2 is negative 18. And negative 18 is certainly less than 0. Thus, the value of x equals negative 1/2 satisfies this inequality, quadratic inequality. Thus, x equals negative 1/2 is a solution. X equals 0 is also a solution of this quadratic inequality because when we substituted 0 for x in the quadratic expression, we get a number, negative 15, that is less than 0. Actually, all the real numbers between negative 5 and 3/2 are solutions of this quadratic inequality. And this closed interval representing the solution of this quadratic inequality consists of infinitely many real numbers. That is, this quadratic inequality has infinitely many solutions. We now take another example. For our second example, consider the following quadratic inequality. We have 6y squared minus 19y plus 15 greater than equal to 0. We want to find the values of y that will satisfy this quadratic inequality. Those real numbers, when you substitute them for y into this quadratic expression, you will get a real number that is positive or greater than 0. As what we did in example 1, we factor out the quadratic expression, and this quadratic expression is said to be quadratic in y because the variable is y and the highest exponent of y is 2. So this is quadratic expression in y. And we factor this out using trial and error. We start by factoring the first term 6y squared. The factors of 6 are 3 and 2, 6 and 1, 1 and 6, 2 and 3, negative 3 and negative 2. And the factors of y squared are y and y squared and 1. But we want a linear factor, so we would use y and y as factors of y squared. And for the factors of 6, I would use 3 and 2. Thus, I factored out 6y squared as the product of 3y and 2y. 3 multiplied by 2 is 6. Y multiplied by y is y squared. Then we factor out the constant term. Because the constant term is positive, you take factors that are both positive so that when you multiply them, the product is positive. Or you take factors that are both negative. Because when you multiply two factors that are negative, the product is positive. Now, 15 has many factors. You can write 15 as 5 multiplied by 3. Or you can write 15 as the product of negative 5 and negative 3. Or 15 can be written as 15 multiplied by 1. Or negative 15 multiplied by negative 1. But I will use negative 5, and negative 3. I will write positive 15 as the product of negative 5 and negative 3. And I chose negative 5 and negative 3 because the middle term is negative. Now, we must decide where to write negative 5, whether to subtract it from 3y or to subtract it from 2y. Now, I will write negative 5 here. I will subtract negative 5 from 6y. From 3y, sorry. We write 3y minus 5. And the other factor we subtract from 2y. We check negative 5 multiplied by negative 3 is positive 15. 3y multiplied by 2y is 6y squared. Now we have to check if we will get the middle term negative 19y, and we do that by cross multiplication. Negative 3 multiplied by 3y is negative 9y. Positive 2y multiplied by negative 5 is negative 10y. Negative 9y minus 10y is negative 19y. Which is the middle term of the given quadratic expression. This means that the factors of the quadratic expression 6y squared minus 19y plus 15 are 3y minus 5 and 2y minus 3. So we now write this quadratic expression as the product of 3y minus 5 and 2y minus 3. And their product, which is equal to this quadratic expression, must be greater than 0 or positive. It is in this product that we would now consider two cases, because the product of two factors or two real numbers can be positive in two cases. One case is that both factors or both real numbers are positive, or both factors or both real numbers are negative or less than 0. We consider case 1. Now you notice that I did not write the equal sign here because in the given there is no equal sign. If this is greater than equal to 0, then you have to write here AB greater than equal to 0. And A greater than equal to 0, B greater than equal to 0. But in the given we only have strictly greater than, thus we do not write the equal sign here. And this is the first case, the product of two real numbers is positive or greater than 0. If A is greater than 0, positive, and B greater than 0, positive. That means the product of two real numbers is positive if both factors A and B are positive, or if both A and B are greater than 0. Where A now is our first factor, 3y minus 5. And it should be greater than 0. And the second factor, B, is also greater than 0 for case 1, where B is the second factor, 2y minus 3, must be greater than 0. And we solve each linear inequality separately, and we take the intersection of their solutions because both the values of y should satisfy both of these inequalities. And we start with the linear inequality 3y minus 5 greater than 0. To solve the linear inequality 3y minus 5 greater than 0, we must have y only at one side of the equation. Thus, we must transpose all the constant terms to the right-hand side of the inequality. And we start by transposing negative 5 to the right-hand side. And when we transpose that to the right-hand side, negative 5 becomes positive 5. And at the left-hand side, we are left with 3y. 3y is greater than negative 5 transposed to the right, it becomes positive 5. And the coefficient of y should be positive 1, thus we divide both sides of this inequality by 3. And the inequality sign greater than will remain greater than because by division property of inequality, if you divide both sides of inequality by positive real number, the inequality remains the same. Or the inequality remains true and the inequality sign remains the same. And 3 over 3 is 1, so we simply cancel out 3 from the left hand side. And we get y greater than 5 over 3. And we represent this in the diagram. This is the solution of the linear inequality 3y minus 5 greater than 0. All the real numbers that are greater than 5 over 3 are solutions. And we represent this in diagram or in the real line. This is our reference point, the origin 0, and because 5 over 3 is positive, it is to the right of 0, and we approximate 5 over 3. And we label this point as 5 over 3. The solution of this linear inequality 3y minus 5 greater than 0 are the real numbers greater than 5 over 3. And because there is no equal sign here, it means that 5 over 3 is not part of the solution. And we indicate that by a small circle. The small circle indicates that 5 over 3 is not one of the solutions of this linear inequality 3y minus 5 greater than 0. And we get that from this inequality because there is no equal sign, which means that y equals 5 over 3 is not a solution. The solutions are those real numbers that are greater than 5 over 3. If this is 5 over 3, the real numbers that are greater than 5 over 3 are the real numbers to the right of 5 over 3. And we indicate that by an arrow going to the right side or going to positive infinity. This is the diagrammatic representation of the solutions of 3y minus 5 greater than 0. The solutions consist of real numbers that are greater than 5 over 3, and those are the real numbers to the right of 5 over 3. Now we solve the second linear inequality 2y minus 3 greater than 0 by transposing negative 3 to the right hand side. But of course, the proper way is to add 3 to both sides of the inequality. By addition property of inequality, if you add the same constant to both sides of inequality, the inequality remains true and the inequality sign remains the same. But the easier way is to transpose negative 3 to the right hand side and it becomes positive 3. And we are left with 2y at the left hand side. 2y is greater than negative 3 transposed to the right hand side becomes positive 3. And the coefficient of y in the final solution should be positive 1. Thus, we divide both sides of this inequality by 2. And the inequality sign remains the same, greater than, because we divided both sides by positive. If you divide both sides of inequality by negative, the inequality sign would be reversed. But here we divided both sides by positive, thus the inequality sign remains the same, greater than. And 2 over 2 is equal to 1, so we simply cancel out 2 over 2 from the left hand side. On the left hand side, we have y now greater than 3 over 2. Thus, the solutions of the linear inequality 2y minus 3 greater than 0 are the real numbers that are greater than 3 over 2. And 3 over 2 is not one of the solutions because there is no equal sign here. Y equals 3 over 2 is not a solution because there is no equality sign here. And we represent the solutions of this linear inequality 2y minus 3 greater than 0 in a diagram. We locate 3 over 2. 3 over 2 is 1.5 and 5 over 3 is Let us check 5 divided by 3. 1, 3, 2. 20 divided by 3 is 6. Thus, 1.5 over 3 is greater than 3 over 2. 3 over 2 is 1.5. Supposing this is 3 over 2. Now, 3 over 2 is not part of the solution of this linear inequality, and we indicate that by shaded circle. But the solutions are those real numbers greater than 3 over 2. If this is 3 over 2, the real numbers that are greater than 3 over 2 are those real numbers to the right of 3 over 2. And we represent that by an arrow going to the right or to positive infinity. This is the diagrammatic representation of the solutions of 2y minus 3 greater than 0. Those real numbers that are greater than 3 over 2, all the real numbers greater than 3 over 2 are solutions of 2y minus 3 greater than 0. For the solution of case 1, we take the intersection of the solutions of these two linear inequalities, because both of these linear inequalities must be satisfied by the values of y. In the diagram, you locate the real numbers that are common to the solutions of this linear inequality 3y minus 5 represented by this arrow, and the solutions of 2y minus 3 represented by this arrow. And the real numbers common to these solutions of these linear inequalities are the real numbers from 5 over 3 up to positive infinity. Thus, the solution for case 1 is the set of real numbers from 5 over 3 up to positive infinity. And we write the solution of case 1 using interval notation. And when you write the interval notation, you start with the left endpoint. In this case, it's 5 over 3. Our solution starts from 5 over 3 and greater than 5 over 3. And the right endpoint, you can see that the arrows go to positive infinity. At 5 over 3, we have a circle, a small circle, which indicates that 5 over 3 is not part of the solution. Thus, at the right endpoint, we use open parentheses. And because positive infinity is not actually a real number, but it is a symbol representing a very, very large positive real number, we also write, at the right endpoint, we write close parentheses. And this is the solution of case 1, the open interval 5 over 3, positive infinity. All the real numbers that are greater than 5 over 3 to satisfy both of these inequalities, and the quadratic expression would be positive or greater than 0. Now we find the solution of case 2, where we take both factors 3y minus 5 less than 0 and 2y minus 3 less than 0. If both factors are negative, their product is positive or greater than 0. For the second case, we now take the factors, both factors or both real numbers, as negative or less than 0. For case 2, the product of two real numbers will be positive if both real numbers a and b are negative. If A is negative and B is negative and you multiply negative by negative, the product is positive or greater than 0. In our example, the number A is the first factor of the quadratic expression given, which is 3y minus 5, and we take the first factor negative, that is less than 0. And this number B in our example is the second factor of the given quadratic expression. So B is equal to 2y minus 3, the second factor of the given quadratic expression, which we now take to be also negative or less than 0. If this linear expression is negative and 2y minus 3 is negative, and we multiply these two, the product is positive or greater than 0. And this is our case 2. And we solve each linear inequality separately, and we take the intersection of their solutions because the values of y should satisfy both of these linear inequalities. We start with the solution. We start solving the linear inequality 3y minus 5 less than 0. And we transpose negative 5 to the right hand side. At the left hand side is 3y. Less than negative 5 transposed to the right, we take the opposite side, it becomes positive 5. The inequality remains less than because we have actually added positive 5 to both sides of the inequality, and the addition property of inequality says that if you add the same constant to both sides of inequality, the inequality sign remains true. And in the final solution, we have to make the coefficient of y positive 1. Thus, we divide both sides of this inequality by positive 3. We divide 3y by 3 and we divide 5 by 3. At the left hand side, 3 divided by 3 is 1, so we simply cancel out 3 from the left. And we get y less than 5 over 3. And these are the solutions of the linear inequality 3y minus 5 less than 0. All the real numbers that are less than 5 over 3 are solutions. And we satisfy this linear inequality 3y minus 5 less than 0. And we represent this solution of this linear inequality in a diagram or the real line. With reference to this point or the origin, we locate 5 over 3 because it's positive. 5 over 3 is to the right of 0. And we approximate that this point is 5 over 3 and we label it with 5 over 3. Now, 5 over 3 is not a solution of this linear inequality 3y minus 5 less than 0 because there is no equal sign here. That means y equals 5 over 3 is not a solution of 3y minus 5. In the diagram, we indicate that by using a small circle or a hole. But the solutions of this linear inequality 3y minus 5 less than 0 are those real numbers that are less than 5 over 3. This is 5 over 3. The real numbers that are less than 5 over 3 are those real numbers to its left. Thus, from this hole or small circle, we draw an arrow going to the left. And this is the diagrammatic representation of the solution of 3y minus 5 less than 0. All the real numbers that are less than 5 over 3, the real numbers to the left of 5 over 3 are solutions of 3y minus 5 less than 0. Now we solve the linear inequality 2y minus 3 less than 0. And we start by transposing negative 3 to the right hand side. At the left hand side, we have 2y less than negative 3 transposed to the other side, you get positive 3. And the coefficient of y should be positive 1, so we divide both sides by 2. And 2 divided by 2 is 1, or we simply cancel out 2 from the left side of the inequality. And we get y less than 3 over 2. The solutions of the linear inequality 2y minus 3 less than 0 are the real numbers that are less than 3 over 2. And 3 over 2 is not one of the solutions of this linear inequality because there is no equal sign here. Hence, y equals 3 over 2 is not a solution of 2y minus 3 less than 0. And we represent this solution of this linear inequality in a diagram. And we locate 3 over 2. 3 over 2 is less than 5 over 3. And we approximate 3 over 2. That's a real number to the right of the origin, or 0. Suppose this is the point 3 over 2. This real number 3 over 2 is not part of the solution because there is no equal sign here, and we indicate that in the diagram by open circle. And the solutions of this linear inequality 2y minus 3 less than 0 are the real numbers that are less than 3 over 2. And this is 3 over 2. The real numbers that are less than 3 over 2 are the real numbers to the left of 3 over 2 from 3 over 2. All the real numbers to the left of 3 over 2 are solutions of this linear inequality. Now we find the intersection of the solutions of these two linear inequalities. And the intersection of their solutions are the real numbers that will satisfy both of these linear inequalities. In the diagram, those are the real numbers that are common to this line, arrow, and this arrow. And those are the real numbers from 3 over 2 up to negative infinity. The solutions common to the solutions of these two linear inequalities are the real numbers from 3 over 2 up to negative infinity. All the real numbers that are less than 3 over 2 will satisfy both of these inequalities. And we write the solution of case 2 using interval notation. Again, you start with the left endpoint, but the left endpoint you can see by this arrow goes to negative infinity. So the left endpoint is negative infinity. And the right endpoint is 3 over 2. Again, because negative infinity is not a real number, it is just a symbol that represents a very, very small negative real number. Negative infinity is not a solution. Hence, we write open parentheses at the left endpoint, negative infinity. And 3 over 2 is not also a solution as indicated by this open circle. or without, as indicated by the absence of this equality sign. So 3 over 2 is not a solution. And we indicate that by using a closed parenthesis at the right endpoint at 3 over 2. And this is the solution of case 2. The final solution for the given quadratic inequality is now the union of the solutions of case 1, which is given by this open interval 5 over 3 positive infinity, and the solution of case 2 given by this open interval negative infinity 3 over 2. But it is customary to always start from the left. Hence, we start with the solution of case 2 and we take its union with the solution of case 1. The final solution now for the second quadratic inequality is the union of the solutions of case 1 and solution of case 2. Of course, you may write open interval 5 over 3 positive infinity union the open interval negative infinity and 3 over 2 because union is satisfies the commutative property. But we write the solution in this way. We write first the solution of case 2 union with the solution of case 1 because it is, as I said, it is customary to start in writing interval notation to start from the left. And at the left we have negative infinity, at the right we have the positive infinity. Now we will check if this solution of the given quadratic inequality is correct. Again, the given quadratic inequality is 6y squared minus 19. Sorry, this is 19y plus 15 greater than 0. And what we did was we factored out this quadratic expression 6y squared minus 19y plus 15. And we considered two cases because there are two ways by which the product of two real numbers or two factors can be positive. That is case 1 if both factors are negative or if both factors are positive. And the union of the solutions of cases 1 and 2 is the final solution. And for this particular quadratic inequality, our solution is the union of this open interval, which is the solution for our case 2, and this open interval, which is the solution for our case 1. Now we represent this solution in a diagram or in the real line. The first open interval is from 3 over 2. The first open interval is the set of real numbers from 3 over 2 and less than 3 over 2. But 3 over 2 is not included in the solution as indicated by this closed parenthesis. And in the diagram, we indicate that by open circle. And all the real numbers less than 3 over 2 up to negative infinity are solutions of this quadratic inequality. The second open interval starts from 5 over 3, but 5 over 3 is not part of the solution as indicated by this open parenthesis. And in the diagram, we indicate that by open circle. All the real numbers that are greater than 5 over 3 going to positive infinity are solutions of this quadratic inequality. And this is the diagrammatic representation of the solutions of this quadratic inequality. The union of this open interval represented by this arrow and this open interval represented by this arrow. Now to check, take any real number that any real number less than 3 over 2 or any real number greater than 5 over 3. Or you can see in the diagram better, take any real number less than 3 over 2 or any real number greater than 5 over 3. I will take x equals 0, 0 is less than 3 over 2. Our variable is y, so I will let y equals 0. And 0 is less than 3 over 2. We substitute y equals 0 in the quadratic expression. We have 6 times 0 squared. Minus 19 times 0. Plus 15. And we want to check if this will give us a number greater than 0. But 0 squared is 0, multiplied by 6 is 0. So this term will go. Negative 19 times 0 is 0. So the second term is also 0 and it will go. Hence, the left-hand side simplifies to 15, which is definitely and certainly greater than 0. We thus conclude that y equals 0 is a solution because when we substituted 0 for y in this quadratic expression, we get a number greater than 0. That is, the inequality is satisfied by y equals 0. Now, I will take a number greater than 5 over 3, any real number to the right of 5 over 3. I will take 2. I will let y equals 2. And we check if it is a solution. In the given quadratic expression, we replace y with 2. We have 6 times 2 squared. Minus 19 times 2. Plus 15. And we want to check if we would get a sum greater than 0 or a sum that is positive. We have 2 times 2 squared is 4 multiplied by 6, 6, 24. Negative 19 times 2 is negative 38. Plus 15. We want to check if the sum and difference is greater than 0 or positive. We have 24 plus 15, that's 39. And 39 minus 38 is 1. And 1 is greater than 0. Thus, we conclude that y equals 2 is also a solution of this quadratic inequality because it satisfies this quadratic inequality. That is, when we substituted 2 for y, we get a number 1 that is greater than 0 or positive. And actually, all the real numbers that are greater than 5 over 3 and all the real numbers that are less than 3 over 2 are solutions. Hence, we conclude that our solution, the union of these two open intervals, is correct. For your practice, please try the following exercises. Solve Show the solution in diagram. Give the solution using interval notations and check. Number 1, x squared minus x minus 2 greater than or equal to 0. The first step is you factor out the quadratic expression. Number 2, 2x squared minus 5x minus 3 less than 0. Again, you factor out the quadratic expression and you consider two cases for which the product of the factors of this quadratic expression would be negative or less than 0. Number 3, 12y squared plus 31y plus 7 greater than 0. Factor out the quadratic expression 12y squared plus 31y plus 7. And then you consider two cases for which the product of the two factors of this quadratic expression would be positive or greater than 0. And for you to be able to check your answer, I give you the solutions for each of the quadratic inequalities. For the first quadratic inequality, the solution is the union of these half open intervals, negative infinity to negative 1. This means that negative 1 is one of the solutions. And this half open interval from positive 2 to positive infinity, where 2 is also included as one of the solutions. This is half open to the left because negative infinity is not included in the solution, because negative infinity is only a symbol that represents a very, very small negative real number. And this is half open to the right because positive infinity is not a real number. The solution of this quadratic inequality number 2 is the open interval from negative 1/2 to positive 3. And the solution of the third quadratic inequality is the union of these two open intervals. The open interval negative infinity to negative 7/3, where negative 7/3, as indicated by this closed parenthesis, is not part of the solution. And this open interval negative, this is negative 1/4 to positive infinity. As indicated by this open parenthesis, negative 1/4 is not part of the solution. To check your answer, you take any real number in these interval notations and substitute that real number in the quadratic expression and see if the inequality is satisfied. And that completes our lesson for today. If you have questions about the lesson today, you ask your questions in the comments below. And don't forget to subscribe to my YouTube channel, Art Kalisan, the channel of learning and leisure. Or you may ask your friends, classmates, neighbors, and relatives to subscribe to my YouTube channel, Art Kalisan, so they may learn as well. Thank you for joining me in my class today in Algebra.